Okay, hello everybody. Welcome to today's discrete optimization talks. Our first speaker for the day is Amitabh Basu. Amitabh did his PhD at Carnegie Mellon and graduated in 2010. And he is currently associate professor in applied math and statistics at Johns Hopkins University. Amitabh mainly works on optimization, especially foundations, and is also interested in applications in data science and astronomy. And today he's gonna tell us about some exciting developments in theory for integer programming. So Amitabh, please go ahead.
Thanks, Elias. And I'd like to thank Alex and Elias for taking this fantastic initiative. I should have attended the talks before, but I'll try to do it more often now that I know where the Google Sheet is. Okay, so I don't want to waste too much time. This talk is going to be on some ideas I've been pursuing for the last year, let's say. I have some things to report that I think are interesting. I hope you agree. This has been work that is joined with Michele, Marco, my two favorite collaborators from University of Padova, and a PhD student at Hopkins, Hongyi Jiang. Okay. So the setting is something that I think should be familiar to all of us. We want to maximize a linear function over some constraints. The first constraint is just convex constraint. So P is just some closed convex set. For this talk, you might, many of the things that I'll talk about, P will actually be a polyhedron. But in general, some results are for closed convex sets. And also, most of the talk will concentrate on the non-convexity S being the mixed integer lattice. But again, there'll be some results that apply to more general non-convexity. So at an abstract level, all I require from S is that it's a closed set. Okay, but it need not be convex. Okay, so this is something pretty familiar. And I'm going to really discuss two classical algorithms for attacking these problems. One is the notion of cutting planes and algorithms based on that. The other is this technique of branchinbound. Okay. And the whole sort of aim of this research thrust is the following, that in practice, neither method is super effective on its own. Branchinbound is slightly better than cutting planes. But really, if you want to solve industrial scale problems, you need to use something called branch and cut, which combines both of these into a very interesting sort of framework of algorithms. And really, the combination works much, much better. Okay, and so the goal is to try to understand this phenomenon. Why don't these individually work? And why does the combination work? And try to do this in a theoretical, quantitative manner. Okay, that's the basic goal. Okay, so I thought that I should review what I mean exactly by a cutting plane algorithm and a branchinbound algorithm, just because I didn't know what background everybody in the audience has. So a cutting plane is a half space or an inequality, depending on whether you like geometry or algebra, is a half space or inequality H that is valid for all your feasible points. Okay, so P intersect S is the set of feasible points that you're considering. And cutting plane is just half space that contains all of that set. And it's usually you want interesting cutting planes. By that, what I mean is that you are actually not valid for your convex relaxation, P, but are valid for the actual integer points or the non-convex feasible points. Okay, so that's a cutting plane, nothing very fancy. And a cutting plane algorithm is something that goes like this. So you usually have something called a cutting plane paradigm. Think about, if you know what this means, think about the Quatal-Gomery cutting plane paradigm or the split cutting plane paradigm. A paradigm is basically an algorithm or a procedure that takes a convex set and gives you a family of cutting planes that you can choose from. Okay, now these may not be all the possible cutting planes as per this definition. Usually it's a small subset of cutting planes like Quatal-Gomery or split cuts. So depending on what paradigm you choose, you'll get a different cutting plane algorithm because you will be using different cutting planes, okay? So no matter what paradigm you choose, what the idea is that you start with your initial relaxation, the convex relaxation, and you solve a sequence of convex relaxation starting with the initial one. You optimize your linear function, you get a point xi, okay? X0 would be the first one. If xi satisfies all your non-convexity constraints, then that's it. You call it a day and you report that's a solution. Otherwise, you find a cutting plane based on this paradigm that you're working with that cuts off this point, xi. You add it to your relaxation, so you get a stronger relaxation and you continue. Okay, so let me just show you this with pictures. So your initial relaxation here is this polygon that I have in black. And I'm generating cutting planes based on this paradigm called split cuts. So split cuts are generated by having two half spaces whose bounding hyperplanes are parallel to each other so that the half spaces cover all your integer points. And then clearly, since all the integer points are covered by these two half spaces, if you look at the two parts of your initial relaxation that are formed by intersecting with these two half spaces, any inequality or half space valid for both sides is a cutting plane. For example, this blue line I have is a valid cutting plane coming from this split that I have chosen here. By the way, here the jagged lines that I'm showing, they are supposed to signify that it goes off to infinity. So these are really two half spaces. Okay. Okay, so you put that cutting plane in, you get a new relaxation, which is this red relaxation now. And again, you would optimize and perhaps you get again a fractional vertex, which doesn't satisfy the integer constraints. And then you might generate another cutting plane, which is this new blue cutting plane. And you get another relaxation and you continue like this. Okay, that's the cutting plane algorithm. You essentially stop once you find the optimal solution of your current relaxation satisfies your non-convexities. Okay. What's branch and bound? Branch and bound essentially divides your initial convex relaxation into smaller convex relaxations. So you look at subsets of your initial relaxation and you sort of go and search in these smaller subregions in an effort to find your optimal solution. Okay, and the hope is that whatever you're leaving out is substantial enough so that this procedure will end after a finite amount of time. Okay, so I'm not gonna really, I've written this down just because if the slides are available, you might want to look at it. But let me just show you with pictures what happens in a branch and bound algorithm. So again, it's the same instance that I was working with earlier. And now, instead of trying to convexify both sides of the split, I'm actually gonna just say that now my new problem is two separate problems. Okay, I'm gonna first optimize on this side. I'm gonna also optimize on this side and pick the best one, essentially. Okay, now the way you sort of do that enumeration, there are many clever heuristics you can play with, but that's basically what's going on. Okay, now, so let's say you go to the right side, okay, and you want to optimize that again. You might end up with a fractional solution. What you would do again is pick some kind of a disjunction, okay, and divide it into smaller parts again. So you kind of build this sort of tree-like structure where you had your initial relaxation at the root, and then you keep subdividing into smaller and smaller subregions, which are guaranteed to contain the optimal solution. Okay, this is basically what is going on. Okay, so that's this. Hopefully, this was all just review. What's the main computational overhead in either of these ideas? It's the number of convex relaxations that you need to solve. That's basically what is the most expensive part of any of these algorithms is. In cutting planes, you add a cut, you solve the LP again, you add another cut, you solve another LP. So the LPs you're solving takes most of the time. Again, in branch and bound, you have these smaller subregions that you're optimizing over, and that's what takes the most amount of time. Okay. Now there are two aspects to this. Firstly, the number of linear programs or convex programs that you have to solve in either of these algorithms, but also you also want to keep track of the complexity of the linear program. So think of a branch and bound tree. You might have a small tree, but all the LPs are super dense LPs. You might prefer a branch and bound tree which has more nodes in the tree, but which has sparser LPs at every node. Okay, so you want to trade off the number, or rather not trade off, but at least keep both of these factors in mind when you're trying to measure the efficiency of these algorithms. Okay, so it's very difficult to say what this LP is harder to solve than this particular LP. This is a very complicated question. So for theoretical purposes, I'm going to focus on this one concrete measure, which is the sparsity of the constraints that go into an LP. So if I have an LP with lots of dense constraints, and by density or sparsity, I just mean the number of non-zero coefficients in any inequality in the LP. Okay, so if you have sparse LPs, these are generally easier to solve because of numerical algebra algorithms that are easier to handle with sparse linear systems. And dense LPs are considered bad. Okay, so that's something to keep in mind. So I have results along both of these directions, but let me first focus on just the first aspect of the number of LPs. So let me forget about the complexity of the linear programs that are showing up. Let me just focus on the number of LPs that I need to solve a particular problem. Okay, and for this, there is a very nice idea for analyzing the number of LPs that show up in any cutting plane or branch and bound algorithm. And this is the notion of a cutting plane proof or a branch and bound proof. Okay, so the idea is very simple. Suppose you want to show the validity of some inequality Cx less than equal to gamma. C might be the objective direction, in which case you're proving that gamma is an upper bound on your problem. Or you might be interested in proving the validity of some other inequality that is valid for your feasible points. Okay, a cutting plane proof based on a particular paradigm, script C, is basically a sequence of cutting planes H1 to Hk such that you generate Hi from the previous relaxation when you add H1 to Hk minus 1 to the relaxation. Okay, so you have P, you generate a cutting plane H1. Okay, that's the first inequality in your proof. Then you take P intersect H1, you generate a cutting plane H2 for that new relaxation. And you similarly keep iteratively generating H3 all the way to Hk. And if the inequality you started with Cx less than equal to gamma is valid for the final relaxation, then we say that H1 to Hk is a cutting plane proof of the validity of this inequality. Okay, it's very similar to the notion of a proof in logic, where you want to prove a certain logical statement and you have certain axioms and rules of inference that you can use to arrive at that. In fact, there is a lot of connection to logic and cutting plane proofs and branch and bound proofs that I may not have time to get to at the end, but if I do, I'd like to comment a little bit on that. Okay. And a branch and bound proof is very similar if it's based on a family of disjunctions. So let's say you stick with split disjunctions or any of your favorite family of disjunctions. And then you say that, okay, you start with your initial relaxation, you apply the disjunctions to make your branch and bound tree. And when you look at the leaves of the tree, the inequality Cx less than equal to gamma is valid for all of them. And so this is now a concrete proof of the validity of that inequality, because all the disjunctions were valid that created the branch and bound tree. Okay, so let me just pause here and ask if there are any questions about the notion of a cutting plane proof, branch and bound proof, cutting plane algorithm, branch and bound algorithm. Okay, Alex, are you looking at the chat in case somebody types in their question? Okay.
But for now, nothing.
Okay, all right, good. So why is this useful, this notion of a proof, apart from its connections to logic that I may or may not be able to get to, is that it helps you analyze the complexity of an algorithm if you're just interested in measuring the number of LPs that show up, forgetting about the complexity of the LPs. If you're just interested in keeping track of the LPs that you have to solve, then if you have any cutting plane or a branch and bound algorithm, you can convert that algorithm's execution into a proof, which would be a cutting plane proof or a branch and bound proof. Okay, so if you can prove lower bounds on the size of any cutting plane proof or branch and bound proof for your instance, that would be a lower bound on the efficiency of any algorithm that solves that problem. Okay. But there could be a gap here, and this is something I might get to at the very end. There might be instances where all cutting plane proofs are very short, but any cutting plane algorithm actually takes a long time, because cutting plane proofs, if you look at the definition, they do not insist on cutting off an optimal solution. There is no objective in the notion of a cutting plane proof, because the inequality Cx less than equal to gamma might be an arbitrary valid inequality. Whereas a cutting plane algorithm, we insist, always cuts off the optimal solution. Okay, so there could be a gap here, but proof sizes give lower bounds on algorithm complexity in terms of the number of LPs that are solved. Okay, and on the other way around, of course, if you get an algorithm, then that gives you an upper bound on the size of the shortest cutting plane or branch and bound proof. Okay, good. So in the pursuit of our goal to understand the relationship between cutting planes and branch and bound and why they work well together, here is a list of results that we can show. Okay, so let me sort of go through this table very carefully. So the first row of results, which is sort of labeled variable dimension, we should think of that I'm looking at instances where the dimension of the instances keep growing. Okay, and I'm going to give bounds where the dimension plays a role. Okay, so it's polynomial in dimension, exponential in dimension, things like this. The second row is dealing with results in fixed dimensions. So I fix the dimension, but of course the family of instances might get more and more complex because there might be many constraints. The sizes of the input data might grow. And so I'm going to give bounds based on the size of the input data. Okay, all right. So let's focus on that first row and that first column there. So what I'm talking about are 0, 1 convex sets. Okay, and I'm going to look at cutting plane algorithms and branch and bound algorithms based on variable disjunctions. That's what the var dis at the top means. So what do I mean by variable disjunction? So these are special kinds of split disjunctions of the form, I say, since I have 0, 1 problems, which means that the convex set is a subset of the 0, 1 hypercube. My disjunctions are going to be simply of the form xi less than equal to 0, xi greater than equal to 1 for some variable xi. Now for disjunctions or branch and bound, that's just a disjunction. So you would go down to faces of your polytope or your convex set. For cutting planes, what this means is that once you look at the polyhedron P intersected with xi less than equal to 0 and the polyhedron P intersected with xi greater than equal to 1, you've got two polyhedra. You're going to take any cutting plane that is valid for both sides of this disjunction. Okay, so I'm basing both my cutting plane algorithm and my branch and bound algorithm on variable disjunctions. And I'm doing this because I want the playing field to be equal for both of them. If I'm going to compare both of them, I don't want to give them one of them more power than the other. So I'm basing both algorithms on the same family of disjunctions. Okay, and CP less than equal to BB just means that CP is at least as good as BB. CP meaning cutting planes, BB meaning branch and bound. Okay, so the formal theorem is the following. If you have any closed convex subset of the 0, 1 hypercube, and S is the integer lattice, so you're really interested in the 0, 1 points. If you use variable disjunctions and you get a branch and bound proof for the validity of any inequality, Cx less than equal to gamma, with k nodes, that means that you have to solve k linear program in executing this branch and bound proof. Then up to any epsilon approximation, I can get a cutting plane proof of the same thing with length at most k. Okay, and it turns out that this epsilon approximation I need only because of nonlinearities. If I assume that P is a polytope, then I can prove exactly the same inequality with a cutting plane proof of the same length. So this is showing that if you have a branch and bound algorithm that solves the problem, there is also a cutting plane algorithm that solves the problem in at most the same number of iterations. Okay. Okay. And then the next part of the result, if you look at that first column and first row, it says that cutting planes actually can be much better. So what I told you right now is that for any 0-1 problem, if you focus on variable disjunctions, cutting planes are at least as good. And now I'm going to show you that they can be much, much better. Okay. So I'm going to look at this stable set instance, which is the union of n copies of triangles. K3 is just the click on 3 vertices. Look at the stable set problem or the independent set problem on this. Find the maximum number of vertices with no edges in common. The optimal value is clearly n because you can take one vertex from each of the K3s. It's not very hard to show that you can convexify each linear programming relaxation with one single cutting plane. And so that you can show a cutting plane algorithm of complexity n, okay? You can just add these cutting planes one by one and you would actually get to the optimal value of n. But on the other hand, if you take any branch and bound proof that uses only 0-1 disjunctions, the variable disjunction, then any such proof is of exponential size. So earlier I told you that cutting planes will be at least as good as branch and bound, and this example shows that there is an instance of stable set problems where cutting planes are order n linear time, but branch and bound is exponential time. And since I have a proof lower bound of exponential, there's that's the lower bound on any algorithm. Okay, so that's that first row and first column. Okay, any questions before I move on in this set of results?
I have one.
Yes.
So do you assume that the cutting planes algorithm has access to, what do you assume about the family of cuts?
So you can do the following. You can take a variable xi and you look at your current relaxation and you do xi less than equal to 0 and take any valid inequality for this union.
Okay, makes sense.
That's all I'm saying.
Yeah. Okay.
But actually, there's these convexifications you can do with Quatal-Gomery also. So this cutting plane algorithm you can implement in many ways. Yeah.
So it's as easy as essentially implementing branch and bound in a way. There's nothing complicated about how you generate the cut itself.
No, because that was exactly the point. I don't want to give my cutting planes more power than what branch and bound has, because then you might be really able to do something.
Right.
Then this theorem doesn't have so much appeal. Yeah.
Makes sense.
Okay, good. Okay, so the second column, I want to go away from 0-1 problems to more general convex sets, but stick with variable disjunction. And in this case, of course, the stable set example is still an example that shows cutting planes can be much better. But the advantage of cutting planes disappears across all instances. There are now instances where branch and bound is actually constant time and cutting planes can take infinitely many iterations to actually solve the problem. Okay. Let me quickly show you this instance. It's an instance in two dimensions, but you can generalize to any dimension you want. There are only 3 feasible integer points. And if you're trying to maximize, let's say in the southeast direction, okay, then the maximum value is 0, assuming that the center point here is the origin. But if you use cutting planes based on variable disjunctions, then it's not very hard to show that you'll keep actually getting closer and closer, but you'll never actually kill off everything. So you'll take infinitely many iterations. Okay. For the sake of time, let me keep going on. I can come back to anything that you guys would like to at the end. So moving away from variable disjunctions. Variable disjunctions are very specific ways of doing disjunctions or generating cutting planes. If you look at more general split disjunctions, okay, by again, that I mean you take 2 parallel hyperplanes, and if you look at the opposite half spaces, they should cover the entire integer lattice. And now you can show that if you allow all kinds of split disjunctions, then branch and bound always does at least as well as cutting planes. That's what I have highlighted in blue in this slide. More precisely, the result is the following. If you have any convex set P and S is the mixed integer lattice, and you use the family of general splits, and if you have any cutting plane proof or algorithm of length k, then there is a branch and bound algorithm that has at most 2 times k nodes in the tree. So up to a factor of 2, you need to, the branch and bound will do just as well as cutting planes. Okay. Now, I don't know whether this advantage can be much better. In the sense, are there instances, either 0, 1 instances or general instances, where branch and bound will do much better than cutting planes if you look at split disjunctions? Okay, I'll come back to this question later. So this is an open question. I don't know the answer to this. Okay, so let's move to the next second row, where I fix the dimension of all the instances. So I'm going to look at all instances in dimension 5 or dimension 10. So the only thing that is varying is the input data. Okay, so I could have lots of constraints, or I could have very big numbers in the coefficients and things like this. And of course, if you focus on 0, 1 problems, then the problem really becomes trivial in fixed dimensions. There are only finitely many feasible solutions, constant number of feasible solutions. You can show that whether you do branch and bound or cutting planes on any kind of reasonable family, you're going to solve this trivially. Okay. So let's go to more general convex sets beyond 0, 1 or beyond constant bounds. And here you can show that branch and bound is again at least as good as cutting planes, but up to a polynomial factor. And the polynomial, the degree of the polynomial is the dimension. Okay, so that's why I need fixed dimension to prove this result. Okay, so more precisely, if I have any disjunction family that I'm going to use for both cutting planes and branch and bound, the size of a disjunction is going to be the number of half spaces that I need to define the disjunction itself. So split disjunctions, the complexity of the split disjunction is 2. Okay. Okay. If the result now says the following, that you take any convex set and you take any arbitrary non-convexity. So this result actually holds for things beyond mixed integer optimization. And if you have a family of disjunctions whose size is bounded by m, meaning that every disjunction in this family has complexity at most m. So for example, splits, complexity is bounded by 2. Then if there's a cutting plane algorithm of size k, or a proof of length k, then there is a branch and bound algorithm, which is of size m times k, where m is the size bound on the disjunctions, to the n plus 1, where n is the dimension. So if n is fixed, this is a polynomial blow up compared to the length of the cutting plane proof. Okay. Okay, and then there are these examples where you can show that branch and bound can be actually much better. And depending on whether you're looking at only variable disjunctions or general splits, it can actually be constant versus exponential or constant versus poly. Okay, where again the exponential in the data size and polynomial in the data size, because the dimension is fixed. Okay, this is the example that you can start with in dimension 3 and generalize with variable disjunctions. You get a proof of length h, which is exponential in the input size, and otherwise you get a proof of length log h, which is polynomial. But the branch and bound proof is constant size. Okay, all right. Sparsity, how much time do I have left? Not much, maybe 2 minutes.
yeah, but then there'll be no questions, and you can take them at 3 right after Ida's talk.
Okay, I'll try to wrap up quickly. So again, so far we have only focused on the number of LPs we solved, and we would now like to look at, the sparsity consideration. Okay, so let me just give you one little result in this direction. I won't be able to talk about everything that we have been looking at. So here's a classical example from 1974 given by Bob Geroslow. Take n to be an odd integer and look at this polyhedron in the 0, 1 set, which is n. If you look at the 0, 1 points, there are no 0, 1 points that satisfy this because n is odd and the left-hand side of the constraint is even. Okay, and Geroslow basically showed, and this was one of the first results showing that branch and bound can be pretty bad. If you use only variable disjunctions, then you need exponentially many nodes in the tree. Okay, there's a very classical result. You'll see this in lots of textbooks. But the disjunction, sum of xi less than equal to n over 2 floor and sum of xi greater than equal to n over 2 ceiling, this solves the problem in 3 nodes, okay? Because both nodes are going to be infeasible in one shot. So what is this telling us? If you restrict the sparsity of your disjunctions to 1, which is basically variable disjunctions, then you need exponential size proofs. But if you have unrestricted sparsity, if you allow dense splits, then you're going to get an order 1, a constant size proof. So we ask the question, okay, what is the trade-off between sparsity and the size of a branch and bound proof, right? And this Hongyi, who's a student, shows the following interesting result. I'm just going to go to the conclusion. It says that if you have order 1 constant sparsity, then you're going to have exponential size proofs. And if you want to get a constant size proof, then you need basically linear density, okay? Otherwise, you're not going to be able to. And the exact theorem is what I stated there, okay? Okay, let me quickly wrap up. Of course, you can talk about what's the effect of sparsity on cutting planes. I'm not going to really say, talk about what we can prove. I will just say that, okay, this has been studied in the past as well by Day and by Shantanu and Marco. And also, I think Alex has been interested in this question. So I think there's a lot of interesting things to think about in this direction. Maybe I'll just leave with this open question that I basically want to use the results that we have to get to the point where I can give you meaningful instances, maybe 0, 1 instances to begin with, where cutting planes or branch and bound on their own take exponential time, but branch and cut, when you combine them, they actually solve the problem in polynomial time. Or okay, even if it's not polynomial versus exponential, there's a clear difference, a strict difference between individual algorithms and the combination, okay? And then of course, there are several open questions that you can look at that are very specific to the results that we had, but let me just stop here in the interest of time.
Okay, thanks Amitabh for a nice talk. So in the interest of time, Alex, please go ahead. And then if you have questions for Amitabh, just stay on at right after Ida's talk, you can ask him in person.